Hello, here is a very basic introduction to finite volume method for CFD applications. We will go through a very simple one-dimensional example and its implementation in a spreadsheet as well as in OpenFOAM. There are a few things that we need to know before we proceed further. The Taylor series is one of them. Using Taylor series, we can compute the values of a continuous function at other values of independent variable if we know the function values at a given point along with its derivatives. And we can go the other way around as well. Given the values of a function at some points, we can compute the derivatives as well. Here the function is known at, let's say, f of x 0, f of x plus delta x, and f minus delta x. We can compute the first derivative using all of these values, giving the central difference formulation, or we can just use another point to get the forward difference formula. Other important thing to recall is the divergence theorem. Given a control volume surrounded by the surface F with a unit normal factor n at the surface, divergence theorem relates the volume integral of a quantity to the surface integrals. These are also termed as fluxes in CFD because they represent the exchange of a quantity along the boundary. This is very useful for finite volume formulation. Consider a very simple heat transfer problem. A bar is maintained at a temperature at one end while is insulated at the other end. At the same time, surrounding air is responsible for convective heat transfer, which we consider as a source or sink term. In order to solve the problem numerically, one need to discretize the domain, which means that splitting the domain in non-overlapping regions covering full domain. Here we have assumed that the heat transfer is dominant along the x direction only, thus giving rise to a one-dimensional problem. Given the transport equation, which is discretized on a generic control volume Vi, we can integrate this transport equation over the control volume, and in this case the first term can be moved from the surface integral to surface integral using the divergence theorem. We can further simplify this surface integral by considering that for one-dimensional problem, the surface basically consists of two faces, in this case the east and west face. So we need to compute this integral at only two faces. So we can write for west face as well for east face the gradient of temperature, and with the dot product with the unit normal at the, let's say, west face and the surface of that face. Similarly, the same holds for the east face. In this case, we know the unit vectors and the surface from the mesh. The only thing that we need to compute further is the gradient at a given face. And in that case, we can use forward or central difference formulation to compute these derivatives. So if we want to compute the derivative at face, each face, we can use the forward difference formulation and can use the temperature at the neighboring cell that is represented by capital E, and the difference between the phase as well and the center of the cell. Or we can use the central difference formulation that relates the temperature in the cell itself, which is Ti, to the temperature in the neighboring cell. Similarly, we can integrate the source term, which is quite simple here, considering that Ti here is the representative value of the cell itself. Now we have all the ingredients to write an equation for each inner node. For example, if we consider here a node, inner node, for example, the term which is the gradient at given phase can be computed for both the east and west phase. We already know how to write the derivatives for for the temperature at each phase, and the next thing that we need to know is the unit vectors E and W, because the surface in this case is unity. And for node 2, we can simply write it in terms of temperature T2 and temperature T1 and T3. The only thing to consider here is the sign for the term, because at the worst phase, the unit normal is always pointing outward in the outward direction for a given cell. Using the same criteria, we can write an equation for T3 as well as for T4. We still need to write equation for T1 and T5, and which is a little bit different because at the boundary we can still compute at the east phase the gradient of temperature using the same formulation as before, but on the other phase we have a boundary condition that specifies a fixed temperature, and in that case we can also use the forward difference formulation between Ti and Ta itself, which are separated by delta x over 2. And then finally we can write an equation for T1 as well. Here we can see the effect of boundary condition as well coming because of Ta. Similarly, for the lost node, we can use the same formulation for inner nodes for the west phase, but for the east phase we have a boundary condition given that the gradient of temperature is 0. So that simplifies a little bit. In term, the gradient divergence term now contains only one term, which we can further expand to get a relation 45. So basically, we get 5 equations for 5 unknowns, and we can invert this matrix to solve this problem, or we can solve it iteratively. So assuming a given value for all other temperatures, we can compute, for example, the value of new T1 and so on. And here is a very simple example in the spreadsheet. So what we only need to know here is to initialize or assume a value for all the nodes at time 0, which is assumed to be 100 in this case. And here you can see a very simple spreadsheet example. For I have assumed a value for each temperature value, and then for T1 we can relate it to Ta, T2 and t infinity. Similarly, for node t2, it only relates to t1 and t3 as well as the ambient temperature, which is here 20, and it remains the same. And then the last node that depends on t4, t infinity, and n. And you can see that after 13 and 14 iterations, we are almost getting the same values. So we are near convergence here. And in that case, we can also have a very simple analytical solution, which is given by this relation. And if I compare that with the values that I got from the spreadsheet, even with this very small number of nodes, we are quite near. So this concludes the first part. In the second part, we will try to run the same problem in OpenFOAM. In OpenFOAM, there are few differences. By default, OpenFOAM is designed for three-dimensional problems, although we can study one-dimensional and two-dimensional problem by using special boundary conditions. In that case, the mesh is always 3D, but if we only have one cell along y and z direction, and if we use specific empty boundary condition, then we can get one-dimensional system. Other than that, we need to find an appropriate solver which represents the same physics, like for example, Laplacian form solves the Laplacian, but it does not contain any source term. So that's why we need to add a source term, and there are two options. We can either use a function object functionality in OpenFOAM, or we can use or we can modify the solver itself to add this source term. For now, we will only consider a function object formulation that is easier and we do not need a recompilation. For OpenFOAM, there are some steps that we follow. That first of all, we need some pre-processing in terms of defining the problem and selecting specific solver in OpenFOAM. We'll have to look and check whether the equations that are there are the one that we need to solve. And it is always a good idea to find some experimental data or analytical solution so that we can compare our results and validate our numerical setup. We still need to process our geometry so that it can be read inside the code, and then we need to create the mesh. On the solution side, once we have the mesh, we need to set the boundary condition, we need to set the source terms, as well as some numerical schemes for divergence, and then the solution parameters for solving the algebraic equations, and then we can run the case. The first thing that we do in this case is to make a mesh, which is quite simple in a sense that we will always make a three-dimensional mesh, but now instead of using many cells, for example 20 here along x, we use only one in both sides, and then we can use this empty type of boundary condition that tells OpenFOAM that this is now a one-dimensional or two-dimensional problem. Other thing that we need to be aware of is that OpenFOAM is a dimension-aware solver, which means that it takes into account the dimension of each variable that we are solving. So in order to be consistent, we need to check if the variable that we are solving are having the same dimension that we want it to be. So in order to check that, we can just go into the source code. In order to check the dimensions, we can see the source code. I am here already in the Laplacian form directory, and if I see there, I can open solver itself. Here we already have some information that the solver is applicable for thermal diffusion in a solid, and also the equation that there is a time derivative of t which equals divergence of dt and then grad of t. And then also the t is the scalar field and dt is diffusion coefficient. In order to check the dimensions of temp t, we can check in the Kjet fields, and here we can see that the volume scalar field is defined for t, but still there is no information for the dimension itself. But it is to be read from the mesh, so from the case file itself. And here I have a tutorial. We can see the volume scalar field t defined here, but still there is no information on the dimension, but it is read from the mesh. So if we go in a case that we want to run, for example here, I can go to 0 directory and read the t, and here we can see the dimensions that we have is on number 4 is for temperature in Kelvin, which is represented by 1 here. And other than that, we can initialize the field to a uniform value of 100. We can also see the boundary conditions here. At one end, we have fixed temperature, and on the other hand is insulated, that is given by zero gradient boundary condition. And in order to check the dimension of diffusivity, we can again go to create fields, and here you can see additionally that the dimension itself is defined and having the dimension of viscosity. And if we do the maths for the derivative of t, which gives Kelvin per second, and then the Laplacian of dt and t, we get the same units in the end. So we now know the units for t and dt. But if we see again the solver, we can see in the equation there is still no source term. But in our case, we have a source, a sink term, and we need to include that as well. In order to do that, we have two options. We can either modify the solver here, and we can modify the equation here and add a source term here, or other option is that we can use the built-in finite volume option functionality in OpenFOAM, where we can write our own source term, or we can also use many of the built-in source terms. In order to use finite volume options, we have to go to the case that we want to run, and then we go to constant finite volume options. Here I am using scalar coded source coefficients, which allows us to write specific code that can be included as source or sink terms. One thing that we note that here we have two types of source terms. One is explicit source terms that does not depend on the variable itself, and then we have implicit source term that depends on the variable that we are solving. And as we can see in the equation, that this additional term n square x is coming because of the sink source term here. If there was no source term, this value would be 0. And in order to get this value, we can use this equation dot diag to get the diagonal part of this Laplacian form solver, and then we can add the term that is n squared times delta x. Delta x here is actually the volume, and the other term that does not depend on the temperature field directly, we can include them in the source term, and for that we can use equation dot source, and then we can add these fixed values there. And with that, we can make the mesh. Here, if we see in the mesh, I'm using only 5 cells in order to match what we did in the spreadsheet. And then we can run Laplacian form. In the first time step, OpenFOAM will compile the coded source term. In this case, the solution is very fast because we are using very few cells here, and we can directly see the results in the last time step, which is 5 here, and look at the T. So in the temperature field, the internal field is the value at each cell, and we can see that it is roughly almost the same value that we saw in the spreadsheet solution, moving from 64 to 21.3. The benefit of using OpenFOAM is that we can easily change the boundary conditions. It would be different. For example, here we can move from zero gradient to a specific flux, or we can use some also here a convective heat transfer. And in that case, you might need to look for mixed boundary condition in OpenFOAM that can be used to study convective heat transfer at the boundary as well. That's all for this video. Thanks for watching.